Assuming that a lot of electricity is produced due to nuclear power generation and there is a lot of electricity left over, what if we mix metal powder such as iron with water to generate hydrogen, and electrolyze the oxidized iron to change it into iron and oxygen? Utilizing surplus electricity from nuclear power generation to produce hydrogen is considered a promising idea. Hydrogen, as a clean energy source, holds significant potential across various sectors and is particularly gaining attention as a key energy source for achieving carbon neutrality. One method for generating hydrogen involves mixing metals such as iron powder with water, a process known as electrolysis. Electrolysis uses electricity to split water into hydrogen and oxygen, making it a viable option for harnessing excess nuclear power. Another approach involves electrolyzing oxidized iron to convert it back into iron and oxygen, known as iron-air fuel cells. While less efficient than hydrogen fuel cells, iron-air fuel cells offer advantages such as ease of fuel storage and transportation. By employing these methods to produce hydrogen from surplus nuclear power, several advantages can be realized. 1. Achieving carbon neutrality. Securing a clean energy source is crucial for carbon neutrality. 2. Resolving power surplus issues. Effectively addressing the problem of excess electricity in the grid. 3. Diverse applications of hydrogen. Hydrogen can be utilized across various industries and applications. However, to implement these methods, several technical challenges must be addressed, including 1. Enhancing electrolysis efficiency. Developing technologies to improve the efficiency of electrolysis. 2. Increasing efficiency of iron-air fuel cells. Advancing technologies to enhance the efficiency of iron-air fuel cells. 3. Developing hydrogen storage and transportation technologies. Creating technologies for the efficient storage and transportation of hydrogen. If these technical challenges are overcome, utilizing surplus nuclear power for hydrogen production could become a realistic solution for achieving carbon neutrality, resolving power surplus issues, and enabling the diverse utilization of hydrogen across industries. However, wouldn't this method prevent ozone layer destruction due to chlorine gas by reacting with distilled water or pure water rather than seawater containing chlorine or hydrogen chloride components? Yes, that's correct. These methods should involve reacting distilled or pure water rather than seawater to prevent the release of chlorine gas and mitigate ozone layer depletion. Seawater contains chlorine and hydrogen chloride. During the electrolysis process, these substances can be decomposed, leading to the generation of chlorine gas. Chlorine gas is a major contributor to ozone layer depletion. Therefore, there is a concern about ozone layer depletion when seawater is used for electrolysis. Distilled or pure water, on the other hand, does not contain chlorine or hydrogen chloride. Consequently, electrolysis using such water does not result in the generation of chlorine gas, offering a solution to prevent ozone layer depletion. In fact, the U.S. Department of Energy, DOE, is actively pursuing the development of technologies that utilize distilled or pure water instead of seawater for electrolysis to reduce chlorine gas emissions. The DOE aims to achieve a reduction of over 90% in chlorine gas emissions from seawater electrolysis by 2030. If successful, such technological advancements would make hydrogen production using surplus nuclear power even more environmentally friendly. However, is there any technology developed to increase the purity of hydrogen generated when mixing iron powder and water and reduce the risk of explosion of hydrogen gas generated at this time? Yes, indeed. There is active development in technologies aimed at increasing the purity of hydrogen generated from the mixture of iron powder and water, as well as reducing the explosion risk associated with the resulting hydrogen gas. Methods to increase hydrogen purity. 1. Adsorption. Adsorbents have a higher affinity for gases other than hydrogen. Therefore, using adsorbents allows the separation of hydrogen from other gases, increasing the purity of hydrogen. 2. Membrane separation technology. Membranes possess different permeation properties for hydrogen compared to other gases. Utilizing membranes helps in separating hydrogen from other gases, thereby enhancing hydrogen purity. 3. Cryogenic separation. Hydrogen has a lower boiling point compared to other gases. Employing cryogenic separation enables the isolation of hydrogen from other gases, contributing to increased hydrogen purity. Methods to mitigate the explosion risk of hydrogen gas. 1. Lowering hydrogen concentration. higher concentrations of hydrogen pose a greater risk of explosion. Consequently, reducing the concentration of hydrogen helps mitigate the risk of explosions. 2. Establishing hydrogen gas detection and control systems. Implementing systems that automatically halt operations or release hydrogen when the concentration exceeds a certain level can prevent explosions. 3. Enhancing safety standards for hydrogen storage and transportation. Strengthening safety standards for the storage and transportation of hydrogen helps prevent accidents during these processes, thereby reducing the risk of explosions. If these methods are successfully developed and implemented, they will contribute to making the production and utilization of hydrogen from surplus nuclear power safer and more efficient.